Okay. So on page 15, we started with an example of a skier who was undergoing 3 different motions. And so reading through the prompt, there was a time frame of constant speed, which has 0 acceleration. And we just assumed that at the top of the hill, this is a skier, a snow skier, so maybe it was a level surface somewhere at the top. And then part 2, or scenario 2, they go down the slope, the ski slope. It's a hill, and they accelerate, they speed up. And then when they reach the bottom, they got to come to a stop. And so even though it's flat, it's not a constant speed, there's constant acceleration to bring them to a stop. And so those are the 3 different parts. And it looks like for part A, we found the skier's speed at the top of the slope, the top of the hill. And even though that's the initial of the second, recognize that it's a transitional speed from part 1 to part 2. And so maybe next class, you solve for the final velocity of part 1, but it looks like last time we found the initial for part 2. Does that make sense? And so let's keep it going. Question B, what was the magnitude? What does magnitude mean? Just the size, the number, how big, how small, who cares about direction, okay? So what's the magnitude of the skier's acceleration? The real physics variable that we're solving for is the acceleration. When slowing to a stop. And so what portion of the ski slope are we looking at? Part 1, 2, or 3? Where are we slowing to a stop? Part 3. And so we're going to be focusing on part 3. So the acceleration. Now it looks like above, we already kind of deduced, we figured out that, well, if I was going in the forward direction, but I want to slow down, something's got to pull me back or push me back, right? And so a negative acceleration. So we should come out negative. But, you know, magnitude, final answer we circle, doesn't have to be negative. And so we know the time. I'm just going to bring it down here. We know the final velocity is 0. Is this enough to solve for acceleration? Well, let's look at our equation. So y'all got a formula chart on each desk. So share it out, turn it to the equation side, or I've got one pulled up here. I did put one in OneNote as well as Canvas. So if you want to go grab it in OneNote, it's in the content library. And it's 2 pages. So if that's something that you want to print so you can write up all on it, go for it, okay? And so if we notice, the first 3 equations are the kinematic equations. They look a little different. Instead of VI, VF, College Board uses VO. I look at it as original velocity, initial velocity. And then the final velocity is V without a subscript. But you're looking at them and you're like, what are all these little X's, right? What are those little X's? Is that velocity of position? Here's where I kind of get ticked off at College Board, because the big X stands for position, but X as a subscript means horizontal. We haven't got into 2-dimension physics yet, but fast forward a week and a half from today-ish, okay, we'll be starting 2-dimension kinematics. Our objects won't just go across the floor, they'll go up and over, like a football, soccer ball, whatever, right? Throw a paper wad. And so that's 2-dimensional, and this little subscript X is just their way of saying you got to have it all in the same dimension when you use these equations. So for right now, ignore the X subscripts, okay? Just ignore them. We don't need them. And so that first one is our VF equals VI plus AT, and so on, okay? And so with these equations, do we have enough on the skier question, knowing the time and final velocity, do I have enough to find the acceleration? We do not. And if you look at the equations, not only is acceleration in all of them, but also notice initial velocity is in every single equation. So you need acceleration and initial velocity either given or something that you're solving for to use any three of these equations. And so with that initial velocity, how am I going to find the initial velocity of part 3 if they don't give it to me? Right, it's another transitional speed. It's equal to the final velocity of part 2. Now we still don't know that, but moral of the story, I got to find that one first and then find the acceleration of part 3. Now notice I'm starting to use some more subscripts here. I'm going to be working with second part and third part, so be careful as you do it. You don't have to add the subscripts, but maybe you're saying, well, step 1, find the final velocity of part 2. And so all that information from part A that we did was all about part 2. And so we know everything, but we can use the first or the third equation. And let me flip back to it. Do y'all want to use the first one with no square or the third one that has squares? And everybody says the first. The first is the most go-to. If I can use the first one, why square if you have to, right? And we don't need to use the third one, but just know you could use the third one, okay? And so I'm going to say VF for part 2 equals the initial of part 2 plus the acceleration of part 2 and the time of part 2. That's not a requirement that you use all those 2's. I love subscripts. They help me keep things organized and straight. And so my habit is to sometimes double subscript as I'm doing here. And so the initial velocity of part 2, that's what we found up above, right? 4 meters per second. Plus the acceleration of part 2 was given to us 2 meters per second squared. And then careful, that's a t subscript 2. It's not a t squared. So know when to square time and when not to. The time of the second part was 6 seconds. Now, every once in a while, I try to include the units just to emphasize that not only are we doing the math with numbers, we're doing the algebra with units as well. And so notice when you have a seconds times a meters per second squared, what happens? Seconds in the numerator, second squared in the denominator. Right, it becomes meters per second, which it should, because you have to add apples and apples. Meters per second plus meters per second, that makes sense. And so now for the easy numbers, we get 12 plus 4 or 16 meters per second is the final velocity of part 2. And it now becomes the initial for part 3. So I'll switch back to red. Oops. And so now we know the initial is 16 meters per second. And by the way, we got a positive. I had defined our positive direction as forward. Even when you go down the slope, the hill, forward is positive. And so now we should have enough, but now using the third interval information. And so knowing both velocities, time, looking for acceleration, what equation will we use to find this A3? Which equation? Same one, but watch out, the different numbers go different places. So step 2 is to find that A3. I'm going to use the same equation, but this time with third parts information. So final velocity in the third segment, well, we're coming to a stop, so 0. Initial is the final from before. Acceleration is what we're looking for. And time, they told us it took 10 seconds, an additional 10 seconds. And so to solve for A, you need to subtract the 16 and then divide by 10. And we should get a negative, which we predicted, and then 1.6 meters per second squared. Now I'm going to circle that number, but technically, couldn't you also give the magnitude, the absolute value of that as your answer? Yeah, but here's why I'm keeping it, okay? We're about to use it to find something else in the next part. If you plug in a positive number into the next part, you're going to get a wrong answer. So yeah, they asked for magnitude, but in real life, it is a negative acceleration, and sign matters, okay? Direction matters. Okay, last question. What is the total distance traveled by the skier? Total distance. Well, sometimes we have constant speed. Sometimes we have positive acceleration. Sometimes we have negative acceleration. I can't just put all those together. Treat it as separate. D1 plus D2 plus D3. This equation is not on the formula chart. It's just knowing there's 3 parts that add up to a total distance. We were given the distance of the second part when it travels down the slope, right? We know that's 60 meters. And I think that's all we were given, right? So how are we going to find the other 2 distances to get a total? Okay, so for part 1, for D1, what do we know? They told us the timing of 1, I think, was 20 seconds. And they said it was a constant speed. So what's your acceleration if you have constant speed or constant velocity? 0. Do you think we're going to use our new constant acceleration equations if acceleration equals 0? Probably not, but watch this. You can. Watch this. What if I use the second equation? What if I use the second equation, but acceleration equals 0? What's 1/2 of 0 times 20 squared? 0. Doesn't the whole 1/2 AT squared zero out? And so a lot of times in physics, we show that with the diagonal arrow and show it zeroing out. Look what's left. If you were to rearrange that and divide both sides by time, you'd get velocity equals distance or distance divided by time. Isn't that basically the defining equation for speed and velocity? And so either use the defining equations for constant speed or zero out the 1/2 AT squared, and there's your equation. And I like this one because it's solved for distance, displacement, which, by the way, in this problem today, distance and displacement, same thing. The skier doesn't go back up the hill, doesn't change direction, so it's same. And so to find D1, wait, do I know the initial velocity of part 1? They didn't tell me that. How am I going to know the velocity of part 1?
Constant speed.
It's a constant speed. Does that mean it's 0?
No, it's the same speed when we started part 2.
There we go. So the velocity of part 1 is constant. It equals the initial velocity of part 2. And so we found that earlier to be 4 meters per second. So now I'm going to use that 4 meters per second as my constant speed in part 1. And notice I didn't put initial or final, I just said constant. It is initial, it is final, it is average, it's constant, right? 4, 4, 4, 4, 4, until they hit the hill. And so 4 meters per second for 20 seconds. And we get D1 as what? $80 meters. And so I can plug that into my summative or whatever kind of statement, D1 plus D2 plus D3. And so 80 meters plus 60 meters, only one more to go before the total. D3, the third part, is not constant velocity. There is acceleration, but thankfully we know that acceleration. We know both velocities, we know time. Guess what? We can use the second or third equation. Let me put them up here. Because we want a displacement. So the first equation does not have any kind of position or distance at all. So you can't find distance with the first one. But since we know everything else, we can use the second or third. What do y'all want to do? Y'all pick. Second. So I'm going to be a good physics student, and I'm going to write the equation so the grader knows what I'm doing. So y'all, free response. You want to show all your work. Get in the habit. And honestly, for multiple choice, I would show some kind of work so that if I have to send you a summary of what missed concepts, if all you do is circle an answer, I don't know what you did in your head or calculator, or if you just guessed. So some kind of physics so that I know what direction you're going. And this is all for part 3, right? And so make sure we don't mix it up with other parts. So we're trying to solve for this displacement 3, distance 3, tomato there. The initial velocity of part 3, well, earlier we said that's the final of 2, and we said 16. The timing of part 3, they told us was 10. Now we know, here's where sign matters. So even though question B said magnitude of acceleration, technically it is negative. I better use a negative here in this calculation. Okay? So a negative 1.6 times another 10 seconds. Don't forget to square. Unfortunately, every quiz or test or whatever, someone always forgets to square. Okay? If I can see your work and figure that out, I'll be like, oh, and I'll circle the square. Okay? Don't let it be you. Pay careful attention to square or not to square. That's the question. Shakespeare fans. To square or not to square? Nope. Okay. 10 squared is 100 times negative 1.6. Negative 160, half that. Half of 160. 80, so we get negative 80 or minus 80 there in that last term. And then 16 times 10 and 160 minus 80, D3 is 80 meters. And so we'll plug that into our summative statement. Okay, and now you just straight add 80 plus 60 plus 80 is 220. Oops. 220 meters. Final answer there. Okay. That one took 3 calculations, right? So moral of the story, some physics problems, just 1 calculation. Most probably involve 2. Some require 3. If you want to count that additive of distances as 1. Okay. Questions on our snow skier. And again, these derived equations on the formula chart, you don't have to memorize them. These formula charts on the desk, they will stay there even on exam days. Okay, you just need to remember the defining equations to, pull out as needed. All right, let's go to the zoo. Let's go to the zoo, at least in physics land. A zoo recently acquired a cheetah and made a bad decision of placing it next to the antelope exhibit that is enclosed by an electrical fence. Now, first of all, don't go PETA on me, okay? This is physics land. No one gets hurt in physics land, not even the cheetah and antelope. That electric fence, if you've never seen one or touched one, I grew up on a farm, so I've touched my fair share of electric fences. They're hooked up to 12 volts. I know we're not studying electricity this year. They pulled it out. 12 volts is not a big deal in the range of electricity, okay? The wall outlets, does anyone know what those are? Voltage, 120. What about the power lines outside?
2,000.
Oh, like 200,000, yeah. You don't want to touch those for sure, okay? Now, and we're not getting too deep into electricity here, but electric fence, no one gets hurt, okay? Even in real life, I've touched electric fences. When my sister was 3 years old, I told her to go touch it. Yeah, I got grounded like punishment-wise. She got grounded electricity-wise, if you know electricity. Okay, all good on that? Okay, no one gets hurt in physics land, moral of the story. It's a true story, yes. I got in trouble. Yeah, that's a true story. She was 3 at the time, so she didn't know any better, right? She learned after that. By the way, do you know how to test an electric fence to know if it's hot or not? Touch it, but and don't go Hollywood thinking, but when your muscles have electricity going through them, they contract. So you don't really want to touch it with the palm of your hand and contract onto the wire. Don't worry, it's not like Hollywood where you'll never let go, but you can touch it with the back of the hand, and that way you contract away from the wire. So back of the hand, or make your kid sister touch it, right? No. Okay, here comes the physics. The cheetah is 200 meters from the fence. Well, the cheetah's just walking there 1 meter per second. We just didn't want it to start from rest, okay? You'll do a lot of problems where the object starts from rest and you go like, yay, initial velocity 0. We wanted some initial velocity, not 0. So the cheetah's just walking along 1 meter per second when it sees an antelope and of course begins running towards it. After accelerating for 4 seconds, the cheetah covers a distance of 68 meters and is moving at top speed. The cheetah maintains its top speed for 2 additional seconds before finally seeing the fence and braking to a stop. I guess the cheetah's touched the fence before, huh? Knows I better stop. Luckily, the cheetah stops just in time, nose to fence, narrowly missing a jolting collision. So, I know we mentioned the antelope. The antelope is the one protected by the electrical fence. The antelope is not part of our moving objects, okay? It's really just the cheetah. But similar to our snow skier, there's different motions the cheetah undergoes. So how many motions did we hear? 4? Okay, what 4?
1 meter per second, accelerating, then running at top speed, and then decelerating.
Good. I'm going to cut the first one off. So we don't know how long they were walking at 1. We gave you the 1 meter per second so that there would be an initial velocity. So yeah, I get what you're saying, but the timer begins when they see the antelope and start running. That's how we'll view it, okay? And so we're going to look at 3 parts of the motion. So by the way, I am not an artist. So there's my cheetah. The word cheetah is my cheetah. If you want to draw out a cheetah, go for it. Initially moving 1 meter per second. Tomorrow it could be higher. Tomorrow it could be starting at rest, but it's just already moving. Timer begins. They see the antelope. What happens? The cheetah is going to accelerate. Do we know that acceleration? They didn't give us the value. Hint, hint, we're going to find it. But I'm just going to call this A1, question mark. What else do I know about this acceleration portion of the motion? They go 68 meters. So whether you call it D1 or just, I didn't hear anything about change in direction, right? Maybe later after the electrical fence, narrow miss. What else do we know? 4 seconds. And so T1 is going to be 4 seconds. Now, I'm going to switch color. What happens next? Well, in this acceleration time, they reach a top speed. And if it's top speed, we're not going any faster, right? And so the second portion is a top speed, maintains a top speed for 2 additional seconds. So we know 2 seconds. What's the acceleration if you maintain any speed? 0. So acceleration for the second part is 0. Everyone good there? And then sees the electrical fence, so begins to slow down. So, and by the way, I'm drawing single arrows. You could draw your velocity arrows shrinking in size. Okay, as you read through your e-textbook, hint, hint, wink, wink, right? Read the book, it's never a bad thing to do. They'll show arrows decreasing in size, okay? And so this velocity, whatever it starts with here, I don't know that initial velocity of part 3, but it's going to come to a dot, it's going to come to a stop. So we know it should come to a final velocity of 0. I don't know that acceleration. Do I know anything else after the cheetah begins slowing down? No, we know very little. All we really know is the final velocity is 0. We do not know time. We do not know a distance. Guess what? We'll find it later. Okay. So even though it feels like we don't have enough, save part 3 for find other stuff first. And end timer. Timer ends when the cheetah reaches the electrical fence. Good deal? Okay, first question. What was the cheetah's acceleration as it began running? Ranning. I don't know if I've ever said that in my life. Whatever. So what part are we looking at? Began running, we're looking at part 1. Part 1. And so the given information is just up above. Is that enough to find acceleration? And sometimes this is the hardest part, figuring out what equation to use. And so notice we know initial velocity, distance, and time. What do we not know? What is not needed to solve this first problem? If we look at our equations, can we use the first one to find the acceleration? Distance is not in there. Do we know final velocity for the first segment? No. And so we need an equation that doesn't need final velocity. We'll look at second or third. Which one doesn't need final velocity? Which one doesn't need final velocity? The second one. And so there's no VF or V is their final velocity. Notice what the last one doesn't have. What variable does the last equation not need? Time. And so just, we write down given, we know what we're looking for. Those are required. But whatever that missing variable is, it's not that it equals 0, it helps us to figure out what equation to use. So it's a little problem-solving strategy. And so to solve for the first part's acceleration, we don't know the final velocity and we don't need the final velocity if we use the second one. And so that's what I'm going to write down. Again, a good physics student shows the grader what physics model we're using, right? Now this one gets ugly, solving for acceleration. I don't commonly do this. In May, you'll probably do algebra without numbers. You'll have to solve this equation for A without any numbers. So I'm going to do it once, but usually with this one, it gets just ugly. So I usually just plug numbers in. But let's do it once, right? Pretend it's a variable solve. What am I going to do to isolate A? Go through the algebra steps. What's first? You don't divide by 1/2 yet. I don't know the exact math rule, but save your 1/2 AT squared for last. What can I do with VIT term? Subtract it to the other side. I don't know what math calls this, but let's subtract VIT. And that equals 1/2 AT squared. Now we can divide by 1/2 or multiply by the reciprocal, multiply both sides by 2, right? So multiplying both sides by 2. But careful, you want to use parentheses there on the left. That 2 goes to both. And then the last step to solving for t squared would be, solving for A. What are we going to do with t squared? Not yet. Divide both sides by t squared. And I would just leave the t and t squared. I wouldn't try to reduce that. Just leave it, okay? If it doesn't reduce easily, you don't have to take it to the, very end algebra, okay? And so even though it looks yucky, there's your equation for acceleration. Most people, me, myself, next time, we'll just plug some numbers in, okay? Since we know them. So acceleration, 2 times the displacement for part 1, remember they gave us 68 meters, minus the initial velocity was given as 1, and the time of part 1 was given as 4 seconds, all over that same time, but this time don't forget to square. And so 68 minus 4 is 64 times 2 is 128 in the numerator, and 4 squared on the denominator is, and if you divide it out, 8. And we do come out a positive. Should we get a positive acceleration?
Yes.
Yeah, they're speeding up in the forward direction. Forward is positive. So they go from 1 meter per second and they speed up. It should be a positive acceleration. Good deal? Okay. B is supposed to say, what is the cheetah's top speed? I see it every year and I forget to change it. That's supposed to say speed. Okay. So the top speed, well, that's the final of part 1 or the initial of part 2. We just had a bunch of part 1 information. Can I just solve for final velocity now? So part 2 I had as red. The velocity that's constant for part 2 is equal to the final velocity of part 1. So I'm going to switch back to blue, part 1. Let's solve for final. Now the first equation, I think we've seen it used many, many times, right? Let's get some practice with that third equation. So I'm going to use the third equation here. And so it's VF squared equals VO squared, or VI squared, plus 2A delta X. And all of these, we said we're going to look at part 1. If you want to put a subscript for all the ones, just to remind yourself, yeah, we're solving for a part 2 answer, but it's the final velocity of part 1, okay? So it's already solved for VF, but I'm going to leave the square for now. Initial velocity of part 1, that was the given, 1. I'm going to keep the squares just to, you know, I don't know what word I'm trying to say. For the norm, it's not always going to be 1, right? So be ready to square whatever the initial velocity is. And then plus 2. We now know the acceleration is a positive 8. And the distance for part 1 was 68. Right? And so whatever 16 times 68 is, someone grab a calculator or pull it up on your laptop. And don't forget to add the 1. Let me know what you get. Say it one more time. 544, and that's after you added the 1? Okay, so we get 544. Is that the final velocity? No, you're not. What does this equal? Doesn't equal VF, it equals VF squared. So how do we solve for VF? A lot of students forget to take the square root. And so when you square root both sides, now we get a final velocity. And true story, y'all, it should come out plus or minus. When you take the square root of a number, plus or minus. Oh, that 544, you now say is wrong. What is it? 1089. Okay, hey, better to make the mistakes today, right? Learn from our mistakes for today so that we don't make them tomorrow, the elusive tomorrow. Okay, so now the number's straightened away. So now we got to square root that. And as someone clicks that in and gets our answer, numeric, let's talk about the plus or minus. The calculator is going to spit out a positive. Now today, our cheetah is only moving in the positive direction. It should come out a positive answer. But, you know, later today, next class, we're going to be throwing things up. They come down. There is a direction consideration. And so just because the calculator spits out a positive, I don't want you to make a bad habit that, oh, the calculator knows physics. The calculator does math. You do the physics. You ask yourself, should that final answer be positive or should it be negative? Now again, cheetah's only going forward, so it's going to be a positive number. Just make that your habit to consider. All right, did I stall long enough? Do we have an answer? Square root of 1089 is? 33. So 33 meters per second, and it's going to be the positive term, okay? And by the way, later on, when we square root time, time is never negative. Okay, always choose the positive value. Good on part B? Part C. What was the cheetah's acceleration as it stopped? What segment? The third. The third. And so we're looking for the acceleration of the third. And we know final velocity. It comes to a stop. And We don't know time, we don't know distance, and we don't know initial velocity. Oh, Miss Earhart, I don't have enough. I can't solve it. Impossible. Move on. No, do the physics. What else could we figure out first?
The distance is from the fence.
Right, and so they told us, so to get D3, they told us a total distance. What if I subtract D1 and D2? Won't I know D3 then? So the total distance is that 200. D1, they told us was 68. D2, wait, I don't know D2. Oh, I guess it was impossible, can't do it. But wait, go up to D2, part 2. That's the top speed with 0 acceleration. Can't we find D2? Do I know the velocity that was top speed? Yeah, we found it to be what? 33? So if I know this top speed is 33 meters per second, and it happens for 2 seconds, aren't we basically doing the displacement of 2? And then that, once again, 1/2 AT squared zeroes out. It got scrunched there. Or go back to the defining equation for average velocity or speed. Distance over time, solve for distance. And so 33 meters per second times 2 seconds, we get 66 meters. That's our D2. Good. Okay, getting warmer. Now do your subtraction. What's 200 minus 68 and 66? Yeah, I think it also comes out 66 meters. Okay, so we've done a couple calculations. And I'm still not at the final answer, but we're so close. So we know final velocity, we know the distance traveled, but all the kinematic equations need an initial velocity. So how am I going to know the initial velocity of the third segment if they didn't give it to me? It's equal to the final velocity of 2, which we said was not 0. They both can't be 0. For segment 2, it was that top speed, the constant 33. And so now using physics, we know the initial velocity. Now we should be able to solve for the acceleration. Now we don't know the time, but that's okay. Which equation does not require time? The last one, it's probably the least favorite. And so using the last equation with part 3 information, we're solving for A3. Again, to solve it, the algebra just looks a little different, but 0 squared placeholder, right? It won't always be 0. Initial velocity was at 33. Don't forget to square it. Plus 2 times, there's the A3 we're looking for. And we found that the distance for the third is 66. So to solve for A3, it would be 0 squared minus 33 squared. Wait, do I square the minus? Do I square the minus? No, I would square first and then subtract, or know that it should come out a negative acceleration. We're slowing to a stop. And if you square that negative, you get a positive. Now, most students are going to be like, insert negative, but know why, right? So don't square that minus. And then whatever 2 times 66 is, will go in the denominator. And so work it out. This one should give you a negative. What is the acceleration? And this one's not a nice you know, I mean, it's kind of nice. It's not just a single number. What do we get? What? Well, what is the answer? 8.25. That sounds familiar. And then meters per second squared. Notice I didn't use my units in the calculation. So if you don't do that to see what cancels and what you end up with, make sure you know what it should come out. As long as everything's SI unit, you should come out SI unit. And so negative 8.25 meters per second squared. Okay, now that we know quite a bit, part D, I'm going to take a break with the microphone. Y'all are going to solve this one. It should be more than one calculation. How much time passed from when the cheetah saw the antelope, time begins, to when the cheetah came to a stop next to the fence, end time? So y'all find the time for the whole thing, total time. I'll give you a couple minutes. All right, y'all get an answer? What was your total time? I hear 10 seconds. Any other votes? How many? 14 seconds I hear. So 10. Well, we're not going to vote, but you know, just do I get another time? Okay, so hopefully those aren't random numbers. Hopefully you actually calculated them. And so one of them's right, one of them's wrong. Let's figure out which. And no, I'm just not going to go to the key or tell you. And so hopefully you did something like T1 plus T2 plus T3. And T1 was given, I think, 4 seconds earlier. And then T2 was 2 seconds. So before you could get a total time, you had to solve for the time of the third. And we had just spent some time with the third part. We know everything but. And so to find time, either the first equation, second equation would get tricky, because with t and t squared, you'd have to do the quadratic. No, not that we won't ever do the quadratic, but I try not to if we don't have to. And so let's look at T3 with the first equation. Plus AT. And so final velocity coming to a stop. Initial velocity was at 33 plus a negative 8.25. And so when you subtract 33, divide by negative 8, you should get a positive. Positive time is good. If you get a negative time, reevaluate your physics. Make that your habit. And so what is 33 divided by 8.25? 4. And so 4 would go in here, and 4 plus 2 plus 4 is 10 seconds. Okay. And so the last class had a 14 as well. I don't know where the difference of 4 more seconds came from. I didn't ask them. I don't know where that came, but I would agree with 10 seconds. Good deal? Okay, now to go to page 16, the first one, y'all can do that question another time, or if we have, you know, a couple minutes here or there. I want to spend the rest of class looking at this marble getting tossed up. And so this marble getting tossed up, the last thing I'm going to do is solve, all right? The first thing we're going to do is talk about free fall. Yeah, thank you. Okay, so getting into this concept of free fall. Y'all tell me what free fall is. What do you think it is?
Acceleration is increasing.
Okay, so something's falling, acceleration is in. Okay, so velocity is increasing. I would agree with that. And so if you were to, you know, Zoomers, whoever's watching this video can't see, But when you find something to say, to throw up. I have my little phone person. Oh, we'll take this stuffy eagles, okay? No offense, Tuffy, sorry, I'll try and catch you. Okay, so if I've got Tuffy the eagle, and I throw it up, uh-oh, sorry, Tuffy. What goes up must come down, right? When is the object in free fall?
Right
It's time to
after
go
it
down.
stops.
Where does it stop? So it stops at the top, and so afterwards, it's falling down, it's in free fall, yes? It's also in free fall on the way up. Think about it falling up. Don't define free fall as falling down. Here's how you would define it. When the object is under the influence, who's influencing this? Of gravity. Of gravity. What does gravity do as your object goes up? It's slowing the object down. It's under the influence of gravity. Now let's get technical. When it's in my hand, gravity's working on it. But is it only gravity? No, so it's the split second it leaves my hand until I catch it, right? And so maybe I add only there. Now some of you are like, well, what about air resistance? Welcome to physics land, where we neglect air resistance unless told otherwise. Actually, if you look at the purple formula chart, flip it to the other side, there's 5 assumptions for the exam. And I think number 1 says something like assume 0 or neglect air resistance unless otherwise stated, something like that. Oh, it's number 2. And so assumption number 2 is neglect air resistance unless told otherwise. And so honestly, we don't do the drag coefficient, so we'll calculate with it very, very little. Some questions we'll ask about conceptual. How does air resistance work? Well, hopefully you know air resistance does what to our object? Slows it down, okay? So a parachuter's life depends on air resistance, right? But for our objects that just go a short distance up and down, we can neglect air resistance. And so free fall is not just falling down. I'm going to draw a little sketch. And by the way, we are still doing one-dimension kinematics. Instead of the object going left or right in the X direction, we're just going to go up and down in the Y. We're not combining the X and Y direction till next weekish, okay? And so take whatever object, I'm just going to pick a ball, and we throw it up. I'm not going to draw an eagle. If you want to go for it, go for it. Okay, so I take my object, I'm going to throw it up. 1 second in the air, gravity is already doing what? Once it leaves my hand, gravity starts driving, and it's going to begin. Okay, well, we don't say decelerate. We start slowing down. And so if we go back to those vector magnitudes, okay, so it's going to slow it down. A dot is indicating that it comes to a split second. Stop, so an instantaneous stop. And by the way, whether you call it apex or what, in physics, we call that a max height. That's the verbiage that you'll see on physics problems. The max height. And it doesn't just stay there. Gravity doesn't stop. Gravity is always working. So what happens in the next phase? It comes back down. And the beauty of free fall, now I'm going to shift over so I'm not drawing on top of each other. So it starts at 0 and it's symmetric. Okay, it's symmetrical. Gravity doesn't care if the object's going up or down. It's changing its velocity the same amount every second. And gravity pulls what direction? Down. Even on the way up, the acceleration due to gravity So you can go A subscript G, or you can just say lowercase g. In physics, uppercase, lowercase, sometimes it's flexible, but G is the one time, and if you look on the front of the formula chart, they even give you the magnitude of gravity. Little g is 9.8 meters per second squared. Careful, big G is a very different number. Big G comes later, okay? Little g is the gravity we care about here. So as the object goes up, gravity acts on it down. Traditionally, you can say negative gravity. Notice they don't tell you negative, they give you magnitude, okay? And then what about on the way down? Gravity acts on the object. What direction? As it falls down. Still in the negative, gravity doesn't change. So whatever length of arrow, gravity is constant. Now here's the #1 question missed every year on the AP Physics exam. I'm going to zoom in. When the object is at max height, what's the acceleration? Negative what?
Negative.
Not -0, no such thing. The common missed answer is 0. You come to a split-second stop, so 0. But if you say that, then you're saying gravity quits working on it for the moment. Acceleration at max height is still gravity. Whether you use 9.8 or this problem is going to tell you to estimate to 10, no matter a 9.8 or 10, gravity does not equal 0 at the top, okay? And so acceleration does not equal 0 at any point, okay? So there, don't miss that question on the AP exam in May. They're going to somehow test your knowledge on that because half the nation misses it or more every single year, okay? Okay, so gravity never quits. Always pulls down, even if the object is going up or down, or comes to a split-second stop at the max height. Good deal? Free fall the whole time, falling up, falling down. Okay, let's start solving this problem. A marble is tossed up from a height of 20 meters. So it has an initial vertical position. We don't start at 0. So maybe in my picture, I come over here and at the initial part, maybe initial position is 20 meters. By the way, very common when you switch the axis that you're in, you can turn those X positions into Y positions. It's still position. You do not have to. Notice the formula chart does not have Y's, okay, in our kinematic equations, but you can rewrite them to be, instead of delta X, you can say delta Y. I'll try to do it both ways. So we start with an initial height, and it's thrown, we already know, up at a velocity of 100 meters per second. And they're saying you can use G for 10. If you want to use 9.8, you just work with more decimals. But even on the AP exam, you can use 10. Here's the times when you have to use 9.8. Okay, so just note to self, G equals 9.8. Real life. And so labs use 9.8. Because a lot of times with labs, think about what we do, percent error, percent yield. And if you round up to 10, that's going to make your percentage that far off, okay? And then the second one is for those of you who go to the textbook and maybe try those optional assignments, optional practice. Textbook coding, those are usually based on 9.8, okay? Canvas stuff, we try to keep it at 10. AP exam, you can use 10, even though they tell you 9.8. You're going to show your work, so the grader knows what you're doing, right? Yes,
On that canvas, will it say like you can use?
we try to make sure, yeah. But we also, if there's numerical response, we also try and tell Canvas, give this window of acceptance. And so a little wiggle room on that final answer to help take care of that. It's not gonna make your, final answer, 20% off, maybe 2%, okay? So we tell Canvas, allow a 2 or 3% window of error. Good deal? Okay. And so we've got several things to solve for. I think we'll save those for next time, but there's the introduction to Freefall. It's an application of vertical kinematics, still in one dimension, all right? All right, questions for me?